Good morning, good afternoon, and welcome to our 15th Webinar Wednesday, featuring two of Israel and BGU's best and brightest experts in the field of robotics. My good friend, Professor Amir Shapiro, who I met about 5 or 6 years ago, when he led and coached the first team of engineering and business undergraduate students from Ben-Gurion University to participate at an international EngCom competition here in Montreal, and Professor David Zarrouk, who I first met at BGU during a Board of Governors visit, and who wowed us with all his toys, his robots, and his robotic vision. I knew when I was younger I should have kept up with my mechanics. Shalom and bonjour, and hello to all of you who have registered from around the globe, to be exact: Israel, England, Scotland, France, the United States, and of course Canada. And I just want to let you know that in homage of the start of the NHL hockey season, I am wearing a Montreal Canadiens shirt with the number 9 on the back, which is the number of Maurice the Rocket Richard, the greatest player who ever played hockey, at least in Montreal. We might also have some of our colleagues from the associates offices in Europe, South America, United States, and Mexico. I am Mark Mendelson, Chief Executive Officer of the Canadian Associates of Ben-Gurion University, and it is once again my pleasure and honor to be moderating today's program. I am thrilled to tell you that we have once again well over 110 registered participants for the webinar, and we expect even more to watch us live streaming on Facebook like we had last webinar. My staff, our lay leadership, and I spend many hours discussing which experts and from which field to invite from BGU, and I believe that so far we have chosen very wisely, as each webinar has really resonated with our supporters and friends. So on behalf of all of us in Canada, the Canadian Associates, I welcome you and thank you all for participating. I must say that this is just another feather in our Canadian cap of successes during these difficult COVID times. Our format today will be very similar to our other webinars. I will first introduce Professor Shapiro, and after Amir finishes, I will then introduce Professor Zarrouk. Each will speak for about 15 minutes, and I will give them a 2-minute warning before they are to finish their presentation. As usual, my colleague and second newest member of our team, Galit Solomon, Director of Marketing and Communications, who started with us about 2 months ago and has already had a profound effect on our communications and marketing strategy and results, will take over with the question and answer period. Zach Ostrov, Executive Director of Winnipeg, will once again resume his duties as Chief Resident Techie of our team, CRT. For our listeners, whoever has comments or questions, you will see the icon at the bottom of your screen, which you can please click at any time and put in your question. Remember, the topic today is advancement in robotics and how Ben-Gurion U is quickly becoming a leader in the development of robots for a multitude of uses. And these two brilliant guys are at the forefront of our incredible advancement in the field. And just a little fact before we start, 1/3 of all engineers in Israel graduate from Ben-Gurion University. It is now my honor and pleasure to introduce Professor Amir Shapiro. He received his bachelor's, master's, and PhD from the Israel Institute of Technology, also known as the Technion. He is currently an associate professor and director of the Robotics Lab at Ben-Gurion U in the Department of Mechanical Engineering. He did his postdoc at Carnegie Mellon, which is very close to where Professor President Danny Shamovitz hails from, and is an expert in just about everything and every kind of robotic movement and development. Amir, the computer is all yours. Amir.
Thank you. Yes, just a little difficulty for sharing the screen. Yes. Now you see my screen? All right, so I'll be speaking about robot grasping and manipulation. Grasping is something that we are doing without even thinking. It's something that we learned when we were just babies. And now it's very easy for us. We have a very complicated hand, very difficult mechanics, very complex mechanics of the human hand. And now I want to show you how we can do this in robotics how the mechanics of robot hand is different and can do different stuff in robotics. And I'll show various projects in this area that we've done. So first is a project that was introduced to us, a problem that was introduced to us by General Motors, and they have a problem. They have a manufacturing line with a lot of robots. Each robot has an end effector, something like this, that can grasp and hold a specific part in a specific place along the production line. The problem is that if they want to produce different model of car in the same production line, they can't, because they need to switch all these end effectors, all these robots' hands. So they asked us, how can they design robots' hands, end effectors, that can grasp several different parts with different geometries? So we came up with an algorithm that automatically mechanically design the end effector, the robot end effector, the robot hand. So first we get a model of the part, then we search for different kind of grasping possibilities along this part, and if it's feasible, then we parameterize it into a space of feature vectors, and if not, then we search for another possibility to grasp this part. The feature vectors parameters are very simple. For a triangle, for instance, it's just one segment and two angles, and it can be done even in 3D and in the space in 3D, in 2D and 3D, and for any kind of number of fingers or points of contact. So we basically get different, here you see different car doors, different car doors. We parameterize all kind of grasp into these feature vectors space, and then we find similar grasps at those spaces. When we find similar grasp, these are common grasp. It's the same grasp for all the parts. So you see here this same triangle along the part. So this is one. So this triangle is actually the design of the contact points of the end effector, and around that you can simply design the end effector. So we did this in 2D. You see here three kinds of objects, and we computed the common grasp, the same grasp for all of them. And here it is the same grasp for all those three different parts. Here for a 3D parts, not 2D grasp, 3D grasp here. We calculate the same grasp, and you see here the same grasp for all the parts. So it's an automatically designed algorithm for robotics hand, robot end effector. So when we grasp the robot in our hand, sometimes we want to change the grasp in order to do something on the other side of the object. So we need to manipulate the object and hold it in a different way. But we have only one hand, we don't have two hands, and we want to switch the grasp inside our hand. So we came up with an algorithm, we called it a skip algorithm. It is the acronym for Stochastic Kinodynamics Planning Algorithm. And it searched for parameters for the grasp that are optimal in a sense, and can plan the motion of the robot to change grasp. And you saw here how we change the grasp of this ball. We just let it fall, and then move the arm, the hand around it and grasp it in a different orientation. We did also experiments, and this is the experimental setup. And you can see here how we just throw it away, let it fall, and then grasp it in a different orientation, and then a different side of the object is open to the to be dealt with or machine. And we can use this algorithm for different kind of applications. You can see here for planning motion between dynamic obstacles. So you can see here how the robot planned the motion around these dynamic obstacles. And the same algorithm, exact same algorithm, can plan the motion of a car bypassing another cars. So it's a very general optimization algorithm for planning the motion of dynamical systems. And also for throwing a ball to the basket. Same algorithm with a little variations, and we can plan the motion of throwing a ball to the basket. You can see here a simple robotic arm that throws the ball exactly to the basket automatically. Everything's done completely automatically. The robot plans the motion by itself. I'll move on to in-hand manipulation. Sometimes we want to manipulate things inside our hand without throwing them, without releasing our grasp, but using our hand as a joint. So we use some kind of a manipulation here. We move the hand, then break it, and then let the object move with its inertia in our hand. And you can see here how we are doing that. So here the robot is grasping and then holding. You see, moving, then let the object move forward with its inertia, and then hold it and release it in the exact angle. And we can do it for longitudinal regrasping as well, as you can see here. In a second, so we want to move an object inside our hand, throw it up or down, as you can see here, with controlling the motion. We use it here, different kind of control aspects, control laws to control this. And you can see here as well, those are not simple tasks for robot to do, because it has to control the contact between the robot hand and the object itself as well. I'll move forward because it's a little slow. I want to show you the experiment. So you saw the robot throwing the object up this rod from plastic, and then let it fall down to the exact position that we want to hold it. And this is a new area in robotics that we opened in that is called in-hand manipulations, and some other researchers in the world are now working on various kinds of algorithms and controllers to do that as well. Another interesting things that we are doing very easily is holding several items in our hand simultaneously. Like holding two balls in one hand. This, for us, it's very simple, but for a robot, it's not so simple. So if we have one object, it's easy to understand where to grasp it. But when you have several objects, you have to determine how to hold them, which configuration, which is the relative distance between them and place between them. And then you have to calculate the contacts, the contact forces between them. And then you can compute the placement of the fingers and eventually to evaluate the grasp that you get and search for the optimal and best grasp. And I'll show you different examples here. So here we have several triangles, and we add more and more triangles. Then we compute the forces and the contacts between the triangles. And when we see that a triangle is not securely held, then we add finger to this triangle to hold it secure in position. And we also compute the overall arrangement that is secured as well. And you see here the final configuration of those hertz with 6 fingers holding those triangles. And we can do this. This is very general. We do it for hexagons here. And you can see here the arrangement of the fingers around the hexagons to hold them securely. And we also built it, and we printed with 3D printers the hand and those triangles according to the design that you saw before. And you see how it can move, and all the triangles are secured in place.
Amir, 2 minutes.
Okay. And you can see it from the bottom as well. And it's moving and it's secure. Okay, the last thing that I want to talk about it in the last 2 minutes is about P-commerce. P-commerce is a new initiative, a new startup that we want to start. And we're working now with Oasis, BGU accelerator, in doing this and starting the company. So this is a picking startup. We pick your e-commerce products. And the problem is now in the fourth industrial revolution, e-commerce is growing, and we order our stuff home and they get, and you can see a lot, everything is automated and we got our packages home. But how this is done? So everything is automated, and only except of the packaging station. And you can see here, and this woman is just taking an object and put it in a shipping box. And we want to fully automate the whole supply chain. And you can see example from China, and you see many robots there, but there is a person here. You can see here a person taking the package and put it on the robot. This is not a nice job working inside just a square here. So we design a picking tool that can pick different kind of objects with different geometries and weights. The idea is very simple. It will be like a shopping cart, and the robot will go along the supermarket, and you see here, and it uses it move here near the object that we want to take, and then it picks a sticker. Here you see a small sticker, then stick it to the object, and with the sticker we can take very different objects and then pick them, put them in the shipping box. The sticker stays on the box. It's a very small and sometimes even a transparent sticker, and it's written "picked by robot" on the sticker. And you can see here example how it works from our lab. So the robot picked a sticker, and then here pick a coffee bag from the shelf and put it in the shipping box, as you can see here, and release it. And then it takes another sticker to take another item, and eventually you'll get the shipping box into your home with the items inside, with a small sticker on each item. And that allows to automate the picking and packaging station in e-commerce warehouses.
Amir?
Yes, this is our idea. This is our patent, and we are now in a process to commercialize it. Just to finish up, this is the Robotics and Control Lab group. Those are my students, and you can see here the names. Those are the people that are doing all the things that we're doing in the lab. So thank you very much. I hope you enjoyed.
All I can say is I remember watching the Charlie Chaplin movie, and the you know what, if he would have known what was going to happen 60, 70 years later, I can just imagine the movie that he would have made. Absolutely brilliant. Thank you so much.
Thank you.
Now, Professor Zarrouk, Senior Lecturer in the Mechanical Engineering Department at Ben-Gurion. He too received his master's and PhD at the Technion. What is with the Technion? Why not at Ben-Gurion? And was a postdoc scholar in biomimetics and millisystems at the University of California at Berkeley. He has received numerous prizes and awards, as well as a Fulbright Fellowship named after the late astronaut and Israeli hero, Ilan Ramon, as well as many prizes for teaching, excellence in teaching, best lecture, etc. David, the computer is all yours.
Thank you so much. I will share the screen. Do you see my screen?
Yes, we can.
Okay, great. So what I'm going to talk about this evening, in my time at least, is how we design simple robots which are bio-inspired. So we are going for simplistic design of bio-inspired robots for multiple purposes. So the major stuff we work on are medical robots for medical purposes, robots for industrial purposes, maintenance, space, and such applications, and field robots for search and rescue, for example, and other applications. So the first part, which is the medical robots, is we want to go through the body in minimally invasive ways. So the body has many areas where you can send robots through. So you have the lungs, for example, so you can have a robot crawling inside the lungs. You have the cardiovascular system, which is which reaches almost any point in the body. And you have the intestines. So our specific point currently is going for the intestines. We want to develop simple robots, small enough, which can travel in the intestine. So these robots will carry a camera, for example, but it's not only a camera. So it's a robot, a self-propelled robot, which hopefully would be untethered, which means that autonomous in the meaning that it's not connected to external wire. And we want it to travel inside the body. Other things is we want robots to travel where wheels can't. So we work on these two problems. Actually, both the problems, the medical crawling and crawling in where wheels can't perform well are very similar, are extremely similar, and we look at them in a similar manner. So why did we choose for a simplistic design? Actually, first, because it does work better. And, you know, it's very old saying attributed to Albert Einstein, which says, everything should be made as simple as possible, but no simpler. So we need to look at the simplest possible solution, but not simpler than that. And, you know, the famous saying that we should think out of the box. So we have these two mottos, and now the question is, how do you do that? So how do you find the simplest possible thing, which is not simpler than it should be? So we work very hard on this. We look into finding simple solutions and develop them and design robots, unique robots. So in the first project I'm going to talk about here is we want to make a robot that crawls inside the intestines. So we have two ideas. First one is making a wave-like robot, which what you can see here in this figure, which can crawl, which can, we hope that one day we have it small enough that it can be swallowed. And then it crawls inside the digestive system, and then it reaches the small intestine and then the larger intestine. And then you have a doctor, a physician, controlling the robot from the outside. So you look at nature, and here see multiple videos showing that robots are making waves and traveling. So from large robots swimming to smaller swimming robots, and actually snakes, you know, we know that they can travel also over the ground. We thought, so let's try to build a device that makes waves. So we looked into literature. We have many interesting devices in literature which shows not simplistic actually, design that make wave. However, they cannot be miniaturized. One of the reasons is that, for example, if you see here, you have a wave that's produced by many motors, and we cannot make it very small. Other designs, they can make wave, but not pure wave. And these are different examples which are found in the literature. But we wanted a pure wave, something simple which can be made smaller. And we came up with this. So this device is pretty large. It produces a wave by rotating a helix. And as the helix rotates, it moves the links up and down, and that makes the wave. So here you can see the robot traveling vertically. It can also swim by making the wave, you know, by just moving the wave. It can also crawl on different surfaces. One thing, as I said again, this is pretty large demonstration, and this is a smaller one. You can see here in my fingers, and this is a very simple solution in which the helix rotates and the links move up and down. Actually, this is patented by the university. This is our patent. We invented it a few years ago, and we received already a patent in Europe and now in the States. Here you can see the design, and this thing advances. So it can reach very high speeds. We reach 57 centimeters per second, which is much faster than other designs of wave robots. And it can move in different, between different surfaces. Actually, it looks like magically moving, but there are physics. I'm not going to discuss the physics, how it works, but we developed the physics and explanation how it works. Here you can see the size of the robot versus a quarter of a dollar. These are smaller design, which we developed. And we made many experiments and how these things would travel on slippery surfaces and flexible surfaces. So not like just rigid or traveling over a regular terrain. This is a much smaller device, but still a bit too large. As the time advanced, we managed to make things even smaller. Here you can see the device traveling in a flexible tube. This is a work that was published together with my student Lihi Drori. And here we made first experiments inside the intestines of a pig. I'm going to skip now and show you other experiments inside the small intestines of a pig. So the device actually works inside the intestines. It advances, and it also gives the impression that it's alive for some reason. It's not, obviously. So it propels itself very, very well, and it doesn't cause damage to the intestine. So theoretically speaking, we have first primary experiments which show that this system could be feasible. We actually developed a larger version, substantially larger version of this robot, in which we can travel over terrain for search and rescue applications. You can see it's traveling over grass and so on. So this is not for medical purposes. It could be used for search and rescue and other applications. I'm going to skip this for now. A second device, which we also developed for medical applications for the same purpose, is not developing a wave robot, but making a worm robot. So here you see a couple of designs of a worm robot, which is near the battery, the AA battery. The same idea is that we make simple system, single motor, simple thing, which means we can make it even smaller. So where do you get the idea of making such robots? These robots are brought from worm locomotion. Here on the left side, I'm going to show you a small worm. Actually, I want to say this is a vicious worm, which a few months ago fell on my neck, and it bit me very badly, I must say. It looks, it's very, very small, but you know, its hooks are very strong. So until I found it and I removed it, so it made all my neck very, very red. What's interesting about it is that this worm has very cyclic pattern motion. So we wrote the pattern of motion, and we carved it mechanically on the design. And we came up with this design. So here we have a worm robot. This is a kind of earthworm robot, which can advance by moving each link separately. Here you can see that the shaft is rotating and making the thing move. Single motor. This design also, actually these are large design, but this is design also advancing by actuating a single motor. So the thing rotates, and the information and the control, let's say the information control, is carved on the shaft. So this is coding vertically, you put it inside a pipe. And later, because the design is very simple, so we can make it even smaller. And we developed a couple of designs which are more or less the size of a battery. Here you can see a very, very small design. And this is an image worm design. You can see it's advancing also in a curved tube. So I'll advance now to the next design. So what happens if we look at a snake? So we see that snakes have a very interesting way of advancing. So the body moves, and you know they slide somehow over the surfaces, and they move very fascinating, very well. We are very fascinated by their motion. And so what happens if we look at a snake and we try to add a tank to a snake, so like make some combination of a snake-like tank. So we came up with this idea. This was already in the past just a concept. Actually, it looks like the snake game, in which you have you turn right, left, top, bottom. Only here we have more degrees of freedom, so you can move in different ways. So we thought we can do this. So kinematically speaking, this is very, very simple problem, but designing this was much more tricky. So we developed this track robot, having in mind that this robot has here one motor to decide where it advances to, and another motor in the back in which pushes the robot forward. So what happens is, as this thing advances, we can decide if we want to go upwards or downwards. And this is the internal spine of the robot. I'm going to show you now the actual design. This paper won the best paper award of the journal IEEE Robotics Automation Letters for the year 2019. And here you can see the robot, how the simulation, how the robot is advancing in the simulation, and how the actual robot is advancing. So here you saw two possibilities. One of them, if you have a rigid spine track, it would fall. But if we have our robot, which we can descend smoothly without colliding with the ground. And we can also advance. Here you see that the system is advancing over the surface while it's rigid at the bottom. And here you can see is going through the wave of the surface. Here you can see how we can avoid collisions with an object sitting on the ground. So we can simply climb on top of it. Here you can see that a regular track would fall, would not be able to advance. And on the other hand, a system like our system, it can climb upwards and then fall to the other side and it continues. Fascinating similarity between the actual robot and the simulation.
David, 2 more minutes.
So in the two last minutes which I have, I'm going to show you one last example about robotic arms. So robotic arms they work very, very well. And they're very, very fast. We have learned how to use them very, very well. But I want to say that robotic arms are very well bio-inspired. So in the sense that they have not bones, so they have links and they have joints, just like we have bones and links, and we have a hand and a gripper at the end. So we thought, okay, how about building a less traditional robotic arm? So let's say instead of having a muscle or a motor on every joint, let's have one motor that advances along the joints and rotates them. So we came up with this design. It's something we also developed in our lab, and it's also patented. So we have here a motor that travels over the links and rotates them. So instead of having an arm and a hand, an arm and a gripper, so we have a traveling gripper, which can also rotate the joint. So we have two things. So this system has multiple advantages, but obviously is much slower than a regular robotic arm. It can perform the same motion, but much slower. On the other hand, it's extremely more lighter than a regular robotic arm. Also, it's cheaper, and it's also reconfigurable. You can also change it very, very quickly. You can just remove very simply. You can remove some of the links and add other links and so on. So here you can see my student adding 4 links. It took her 30+ seconds. She was doing this fast, but yeah, it doesn't take so much, so long to do. So we thought also we can use it for agricultural purposes. Here you can see the demonstration. You see also picking up fruits and placing them in the basket. Also, we have possibility of space applications. We have some companies interested in using this robot for space applications. Nothing has been finalized, but there is some interest, at least we can see. And so just to say a few last words about what we saw here. We saw that making a better design and making a simple design reduces the cost of energy and makes control much, much easier, but also improves the performance. So we have better performance, less control and energy requirements by using a better mechanical design, a simple design. To finish, I'm going, actually, I don't know how much time we have, but this is a last movie, but I'm not going to run it now because we are out of time. We'll leave it for another time. How do you stop this? Okay.
Love them. I love watching those little toys. They're fantastic, really. And to think of the genius that goes into those simple little robots. Fabulous, David. And now I will turn our question and answer period over to our Director of Communications and Marketing, Galit Solomon, herself born in Israel. Galit, the computer is now yours.
Very good. Thank you so much. Thank you so much, Mark. And what a fascinating 40 minutes we've just spent. We've got quite a few questions to get through. So we'll get started. This first question is actually for Professor Shapiro. It comes to us from David Davis. And the question is cybersecurity built into the robot to ensure that the system is not hacked and is safe? And really, at the end of the day, the robot doesn't end up doing things it's not supposed to.
Well, yes. So each robot is connected to a computer, and each computer is actually secured by a firewall, VPN, encryption, and all kind of cybersecurity measure that we know and can have.
Okay, very good. That's always good to know. Moving on, the next question is for Professor Zarrouk. It comes to us from Charlie Hadid. For the SAW swimmer, is it going to eventually be a wireless controlled system, as what we were able to see in the video is actually a wired control application?
We are looking into wireless system. We have actually smaller designs and longer designs, smaller designs, and different designs, but we foresee it's going to be a wireless system which is controlled externally by an operator, and we think it'll be able to do perform some small medical procedures such as dropping medicine or maybe taking a biopsy. Because if you control the robot, you can run it much faster inside the body. And then you can reach a specific target, take a biopsy, then continue to the next place. And also you can know where the robot is inside the body. So multiple advantages, but it's going to be controlled and wireless.
Very good. And another question here for you, Professor Zarrouk, from Dr. Keith Meloff. He is asking if the object of interest is within the gap. So in that video that we saw, where there were the two benches and the robot going across, if the object of interest is within that gap, could the robot potentially miss it?
Actually, I didn't understand. You are talking about the SAW robot?
That's right, right.
So I'm not sure if I understand clearly the question. So we are looking at something that's one day we're going to swallow. Mm-hmm. It's going to go through the digestive system. It have nowhere to go, so it can't lose its way. There's one way out. I'm sorry,
my mistake. It wasn't the SAW robot. It was the one that went right across the two benches in the video, the white robot that was traveling right across, as opposed to falling into the gap that was in between.
Okay, yeah. If it misses the gap.
It's the grasping robot, I believe, yeah.
So if it's the track robot, so there is a limit for what gap it can cross, but the limit is much larger than the regular track. This is what I can say. So if it falls inside the gap and the gap is too deep, it's gone.
Okay. Let's take it to a high-level question for a moment now. Of course, many of us around the world have been dealing with the pandemic, and it's impacted. Really, there hasn't really been a country that's been unscathed by this. Can we bring that factor back into the robotics world, specifically within Israel, and of course more specifically at CABGU and within the departments where you work? Has the pandemic impacted the field of robotics, and if so, how has it done so? And I'll open that up to both Professor Shapiro and Professor Zarrouk.
Amir, start.
Okay. So yes, actually everyone wants to do something to help with the pandemic, and we as a roboticists, we want to do that as well, and colleagues around the world also are doing that, and we myself and other people as well try to use robots, mobile robots inside the closed departments in the hospitals, specifically in Zarrouk Hospital,
Mm.
to communicate with the patients inside the closed department, and that helped. But eventually the robots were too complicated to operate, and it was easier to just mount cameras and microphones, and that was the end for our robots. But around the world, many robots were developed for the pandemic, for disinfection of areas, using UV light, ultraviolet light, using some kind of sprays for cleaning, etc., and for communication. Yes.
Okay. And Professor Zarrouk, did you have a response to that as well?
Actually, we haven't developed anything specific for the COVID period. We think that robotics, at least some of the robots we are developing, but not ready to go on the market, could be used for deliveries. So instead of going to the supermarket and buy stuff, you can send the stuff to the people without sending humans. But our robots are not right for that yet. But we're looking into such possibilities. For the other question, I don't know if you asked how is the pandemic affecting us. So there's another effect of the pandemic. So some of us are in isolation. So as the larger the group is, you have more problems. So whenever you have somebody who has been contaminated, so everybody has to go for isolation. So I know Amir, his team they had a couple of students, and I'm currently now at home. I'm half isolated. So these things happen. But in general, we are doing our best to keep working. So we have divided the groups into subgroups, so to avoid having such problems. And we are, I would say, maybe 90% working instead of 100%.
Right, got it. Okay. We have another very interesting question. If money was no object, what is your dream project? And I'd like to extend this question to both of you. Maybe we can start with Professor Shapiro.
Well, if money is not an object, then I want to help the humanity to be better in two ways, I think, which are kind of connected. One is having humanoid robots that could do things that we can't and don't want to do, or dangerous for us. And the other thing is for helping humans in medical situations. So any kind of mechanical problems, biomechanical problems, or something like that, or for surgery, for all kinds of biorobotics and medical robotics. That was something that I would like to invest in if I had unlimited money and time.
And it seems like that is something, Professor Zarrouk, that you're trying to do, at least with, I believe it's the SAW robot, is that correct?
Yeah, actually we are looking, actually if money was not an issue. So actually, yeah, I want to proceed further with the robots. So when we develop robots at the laboratories, so we have low budgets and we don't have final products. Mm-hmm. So moving from a prototype, although you see the product is working, but moving from a working prototype, inside the lab to a real prototype, so that costs a lot of money and costs, but not only the SAW robots, so other grasping arms and these things. So we have limitation from moving from the lab to the market. So the university tells me, okay, go find some funding and you can sell it, develop startups and so on. But obviously, we are more scientists than businessmen. So at least me. So it's more of an issue, yeah. But if funding was not an issue, I would proceed much farther with the robots. And actually, we have more ideas than the same. I'm sure also for Amir, we have more ideas than resources. So we had more money. I have many more ideas I want to develop also.
Right, right. Well, you know, you're in a good position if you have some phenomenal ideas coming down the pipeline, just having to find the resources. We have a question from Zach Ostroff, who is one of our executive directors out of Winnipeg. And his question is for Professor Shapiro. He's asking, how far is your robot away from commercialization?
I hope the one for P-commerce, that for picking for the e-commerce industry, I think is not far. It's just a matter of funding, and in less than a year we can have a pilot running.
Okay.
That's the main idea.
And then once you move from the pilot position onwards to actually making it commercial and available to the masses, how long does that process usually take? I mean, I would assume that it's a project by project case, but what would you say?
I would say that after we have a successful pilot, it should be immediately to move to another project, and then another project, and then more, and then the company should be able to support itself instead of having just to be supported. The main problem now is just to get the initial funding to make it run.
Got it. Yeah.
To start.
To get it started, exactly. Get it off the ground. Obviously, many people are fascinated by robots and how far advancements in robotics has come. But then there are also the skeptics or the people who are afraid of robots. What do you say to them? I mean, you are working on creating these phenomenal projects that can really go a long way, and like you said, Professor Shapiro, in helping humanity. But at the same time, there's a sense of fear as well that some people experience. Maybe we'll begin with Professor Zarrouk. What would you say to people who feel a fear around robotics?
Actually, I want to share something that happened recently in our lab. So one of our robots, which I did not present here, it is a robot for climbing on obstacles. So we implemented machine learning on the robot, and then we found a solution so the robot managed to climb over an obstacle. We wanted to see how good it learned. So it learned on its own, right, in the simulation. So we asked 6 students to come and try to beat the solution. So we know, is it a good solution or is it not good? And we found that the robot, the program beat our students. So some people said, okay, because you gave them specific conditions which are not good enough, that's why the artificial intelligence was better. So we gave them regular joysticks and tried to drive it. The performance was even lower. And I want to tell you that for a little bit of time, I was a bit afraid. It gave me a feeling machines are beating us. But I think that I'm not as worried as that, because whenever you can define very clearly a problem, robots and computers outperform us. But in general decision, they are not. Obviously, everything can be used for the good and bad, and so on. Also, knives can be used for for good purpose, cutting apples, or be used as a weapon. Robots can also be used as weapons, obviously. But I'm not afraid that, at least for for any future, I can foresee that they're going to take over the world. This is my personal opinion.
Very good. And Professor Shapiro, do you agree? Yes, I agree. There is a good reason to be afraid of robots, especially military robots. My view on it is just to be in the right side and be more advanced than the other.
Cross our fingers in a sense, or do you feel like it's possible to?
It's possible.
It is possible. Okay, I see, Mark, you're joining us again. Can I just wrap up with one quick question for both of you? I like to wrap up with a look ahead. So what do you think the future of robotics in Israel is going to look like?
Go ahead.
Amir?
I see a lot of investments and advancement in robotics in Israel, in all kind of aspects, from medical robotics to industrial robotics to warehouse automation to agricultural robotics. Many companies are coming up and growing in Israel. So I see a bright future for robotics in Israel and in the world as well. I think it's a good era for robotics.
I totally agree with Amir. I think one of the things about robotics, it's not like, it's not like computer programs and so on that you can build and sell in 1, 2, 3 years. So they take more time. But I think now the market and the industry is much more ripe and much more ready to accept the robots. And I think there's going to be a surge in robots being sold for different purposes, for medical purposes, agricultural, industrial, cleaning, maintenance, all sorts of things. I think now the world is more ready for robots and know how to deal with them. And I think in the next few years, many companies are going to sell robots in Israel.
Very good. Thank you both so much. I appreciate it.
Galit, thank you so much. A great Q&A period again. And Amir and David, every time I hear you guys speak, I just wonder at the brilliance and the fun you must be having in using your algorithms and using your mathematical skills in making these great toys, which are really toys and which help us in our everyday work. And another area where BGU is at the forefront, really, of the robotic design and research. Huge thank yous to you, our listening audience, for supporting us and the outstanding Ben-Gurion U. If you would like to find out more about our university and the research being conducted there, please check us out at www.bengurion.ca. I would really like to thank my excellent staff across Canada, and a shout out to our new executive assistant in Toronto, Elise Mathelon, who just joined us last week. Thanks to my national lay leadership, as well as my excellent colleagues in Israel, President Danny Shamovitz, Vice President Jeff Kay and his team, and my colleague, CEO of the American Associates, Doug Sesserman. Stay tuned for our next webinar on February 3rd, featuring BGU President Danny Shamovitz on climate change and sustainability, another definite areas of our expertise. I would now like to give a shout out to our staff team in Canada for their outstanding efforts in organizing 3 upcoming events, one of which is already sold out, the In Conversation with Israeli Authors, and we have the virtual tour of art at Ben-Gurion University and a joint program with the Israel Medical Association in Toronto. 3 outstanding initiatives, and people are talking about the little goodie basket. Thank you so much to Indigo and the Reisman Schwartz Foundation for their support. And of course, Ben-Gurion, like all world-class universities, relies on its supporters to be able to continue its innovating and out-of-the-box research. And who knows, if you give enough, we'll put your name onto the next robot, and you too will be the next Elon Musk. Only worth 125 billion, 140 billion. From my mouth to God's ears for both of you. Please call one of our offices if you'd like to participate. Until February, I wish you a COVID-safe 3 weeks. Wear masks, keep social distancing. Israel, line up for your vaccinations. And let's hope that in Canada, vaccines will soon be readily available. Kol hakavod to Israel for leading the world and being number 1. Almost 2 million, or I think they have surpassed 2 million vaccinations. And of course, to Ben-Gurion University, MD and PhD graduate, Dr. Tal Zaks, Chief Medical Officer of Moderna. Thanks. Take care, keep well, and see you in 3 weeks.
Thank you so much, Mark, for hosting us.
Thank you
Pleasure,
very much.
guys. Thank you so much for taking time out of your schedule. Fabulous.
Bye.
Thanks. Bye.
Kol hakavod.